The universe is a balance of creation and destruction, a place where stability exists only because nature is constantly fighting to keep itself from collapsing. Every atom, every planet, every star balances on a knife's edge between opposing forces. Push too far in one direction and everything breaks. Stars are no exception. From their birth in clouds of gas to their fiery deaths, stars are defined by this struggle, a perfect equilibrium between gravity pulling inward and pressure pushing outward. To understand what happens when that balance is lost, we begin with the ordinary star, the foundation of everything we know. Inside a star like our Sun, matter exists in its most energetic and unstable form, plasma. This is not a solid, liquid, or gas, but a superheated soup of charged particles. To the naked eye, the Sun's surface appears calm, a glowing yellow disk. But beneath that tranquil light is chaos. The photosphere churns like a boiling ocean, with currents of plasma rising and sinking in endless motion. Each ripple and flare is powered by fusion, the process that has kept our star alive for billions of years. At the Sun's core, temperatures reach over 15 million degrees Celsius. Hydrogen atoms are crushed together under such immense pressure that they merge into helium, releasing enormous amounts of energy. Every second, the Sun converts 620 million tons of hydrogen into 616 million tons of helium. The missing 4 million tons become pure energy, radiating outward as light and heat. This energy provides the outward pressure that perfectly balances the inward pull of gravity. The two forces, expansion and contraction, exist in harmony, locked in a timeless dance known as hydrostatic equilibrium. It took generations of scientists to understand this balance. One of them was an Indian physicist named Meghnad Saha. In 1920s, Kolkata, Saha developed a way to predict how much of a star's matter exists in the form of plasma. His equation showed that temperature and pressure determine how many atoms are stripped of their electrons, a process called ionization. The hotter and denser a star becomes, the more completely it turns into plasma. The Saha ionization equation became one of the cornerstones of astrophysics, allowing scientists to decode the internal structure of stars they could never touch. Using this knowledge, astronomers realized that the visible surface of the Sun is not fully ionized. Even at 5,500 degrees Celsius, it's only partially plasma. To reach a place where matter is completely broken down, you must travel deeper. At the core, hydrogen nuclei are packed so tightly that a single cubic centimeter weighs more than 150 grams, 8 times denser than gold. The entire core has a density greater than anything found on Earth. If you could scoop out a spoonful of this material, it would weigh more than the Titanic. This unimaginable density should cause the core to collapse, but it doesn't, because the outward pressure from fusion pushes back against gravity. The star walks a delicate tightrope, forever balancing on the edge of destruction. For billions of years, the equation of state, the relationship between temperature, density, and pressure, keeps the star stable. So long as hydrogen fuel remains, this invisible equation holds the universe together. But nothing lasts forever. Even the most stable star has a limit. Over time, hydrogen in the core runs out. Fusion slows, pressure drops, and gravity begins to win. The balance is broken. The core contracts, heating up until it ignites helium and briefly restores equilibrium. But the cycle continues, each stage burning faster than the last. Eventually, the fuel is gone. When that happens, gravity crushes the star inward. What follows depends entirely on the star's mass. For stars like our Sun, the collapse stops at an extraordinary stage. As the outer layers drift away into space, forming clouds of glowing gas called planetary nebulae, the core is left behind as a tiny, dense object known as a white dwarf. This star remnant contains about half the mass of the Sun, packed into a sphere no larger than Earth. A single teaspoon of its material would weigh several tons. At first, scientists couldn't understand how such a small object could exist without collapsing under its own gravity. The answer came from quantum mechanics, a new branch of physics that emerged in the 1920s. Among its pioneers was the British physicist Ralph Fowler, who, after being wounded in the First World War, turned his attention to the strange behavior of matter at atomic scales. Fowler discovered that the particles inside atoms obey a rule known as the Pauli exclusion principle. No two identical particles can occupy the same quantum state. In a white dwarf, this rule becomes a shield against gravity. As gravity squeezes the star's atoms closer together, the electrons resist. They can't all occupy the lowest energy levels, so they pile up into higher ones, creating a kind of subatomic pressure known as degeneracy pressure. This invisible force is strong enough to counteract gravity, holding the white dwarf stable. It's not heat or fusion that supports the star now, it's the quantum structure of matter itself. Fowler's insight revealed that even in death, stars find a new balance. But this balance also has a limit. A white dwarf can only resist collapse up to a certain mass, about 1.4 times the mass of the Sun. This is known as the Chandrasekhar limit, named after the Indian astrophysicist Subramanian Chandrasekhar, who expanded on Fowler's work. Beyond that mass, the electrons can no longer withstand gravity. The pressure that once held the star together fails, and the core collapses again. When massive stars reach this point, the results are catastrophic. As fusion stops, the core implodes, triggering one of the most powerful explosions in the universe, a supernova. In just a few seconds, the star releases more energy than the Sun will emit in its entire lifetime. What remains after the explosion is either a black hole or something even stranger, a neutron star. Neutron stars are the densest objects in existence apart from black holes. To understand their formation, imagine compressing the entire mass of the Sun into a sphere only 20 kilometers across. A neutron star is so dense that a single teaspoon of its material would weigh more than all the humans who have ever lived combined. The gravity on its surface is unimaginable. If you dropped an object from a meter above, it would hit the surface at nearly half the speed of light. The creation of a neutron star begins when gravity forces protons and electrons to merge into neutrons. What was once a sea of atoms becomes a solid mass of nuclear matter, a single, gigantic atomic nucleus. The same exclusion principle that saved white dwarfs now acts again, but this time it's neutrons providing the degeneracy pressure. Once more, quantum mechanics steps in to keep nature from imploding entirely. This process marks the boundary between what physics can explain and what it struggles to describe. The densities and pressures inside a neutron star push the laws of nature to their breaking point. Inside, matter is crushed into forms that cannot exist anywhere else. It's here, at the edge of collapse, that we begin to glimpse the true limits of the universe. Even though neutron stars are only about the size of a city, they can spin dozens of times per second, some rotating hundreds of times every second. They emit beams of radiation from their magnetic poles, which sweep across space like lighthouse beams. When those beams cross Earth, we detect them as regular pulses of radio waves, leading to their other name, pulsars. These pulses are so consistent that they rival atomic clocks in their precision. The discovery of pulsars in the late 1960s confirmed the existence of neutron stars, which had previously been only a theoretical idea. They represented the universe's final balancing act before collapse becomes irreversible. If gravity pushes just a little harder, even neutron degeneracy pressure can no longer hold, and the star falls inward into a singularity, a black hole where not even light can escape. But before that final step into darkness, the neutron star stands as the universe's last stable fortress. In a single object, the neutron star unites all of physics, quantum mechanics, relativity, and thermodynamics. It is both matter and mystery, both the product of destruction and a cradle of extreme stability. Inside its tiny volume are the densest known conditions in the cosmos, the very limit of how far matter can be compressed before it breaks the laws of nature. But what truly lies within that dense core is still unknown. We can't recreate its conditions on Earth, and light barely escapes its surface. Yet, hidden inside that small sphere may be the key to understanding how the universe itself holds together. Every neutron star is a laboratory built by nature, testing physics at pressures beyond anything we can imagine. To peer into their cores is to ask one of the most profound questions in science. What happens when you push matter to the edge of reality? The quest to answer that question begins with a journey deeper into these stellar remnants. Because inside their crusts, at depths where atomic structure breaks apart and subatomic particles twist into strange forms, lies the true frontier of physics. It is there, beneath layers of exotic matter and unimaginable pressure, that the universe reveals how far it can be stretched before it finally shatters. And that is where the story of the neutron star's core begins. When a massive star dies, it doesn't fade quietly. It collapses and explodes with a force that can outshine entire galaxies. For a few moments, it becomes the brightest object in the universe. This explosion, called a supernova, is both an ending and a beginning. It destroys the old star, but leaves behind something new, something that pushes the limits of physics itself, a neutron star. The transformation begins when fusion inside a giant star stops producing energy. Gravity, no longer opposed, begins to crush the core. The collapse happens in an instant. As the star's outer layers fall inward, the core is squeezed beyond comprehension. Protons and electrons are forced together, merging into neutrons and releasing a flood of neutrinos. The matter that once made up atoms is crushed into a solid ball of nuclear material no larger than a city. When the outer layers rebound off this collapsing core, a shockwave rips outward. That shock is the supernova. What remains at the center is the neutron star. It's the size of a city, but weighs more than the sun. Its density is so extreme that a single teaspoon of its material would outweigh a mountain. Its surface gravity is billions of times stronger than Earth's. On a neutron star, a pebble would hit the ground at nearly half the speed of light. Even light itself is bent by its gravity, warping the surrounding space like a lens. Neutron stars are not quiet corpses. They are some of the most dynamic and violent objects in existence. Many spin rapidly, completing dozens or even hundreds of rotations every second. These fast-spinning neutron stars are called pulsars because their magnetic fields funnel radiation into beams that sweep across space. Each time one of those beams crosses Earth, we see a pulse of light. Some pulsars rotate so consistently that they rival the precision of atomic clocks. They are nature's most reliable timekeepers, powered by gravity and the remnants of stellar collapse. But as scientists studied pulsars, they began to realize that neutron stars were more than cosmic curiosities. They were laboratories of physics operating under conditions no human experiment could reproduce. The pressures and densities inside them are so great that the behavior of matter becomes uncertain. The laws that work perfectly on Earth may fail inside these stars. The crust of a neutron star is a place of unimaginable extremes. It's only a few kilometers thick, but it's strong enough to withstand gravity that could flatten mountains. Its outermost layer is an atmosphere of hydrogen and helium barely 10 centimeters deep, heated to 2 million degrees. Beneath it lies a solid lattice of atomic nuclei embedded in a sea of electrons. As the pressure increases, electrons are forced into the nuclei, creating more and more neutrons until only a few protons remain. The deeper you go, the stranger the material becomes. Under such crushing conditions, protons and neutrons twist into exotic structures never seen on Earth. Computer simulations suggest these particles may arrange themselves into strange shapes resembling tubes, sheets, or bubbles, forms nicknamed after pasta, spaghetti, lasagna, gnocchi. Physicists call this substance nuclear pasta, and if it exists, it would be the strongest material in the universe, 10 billion times stronger than steel. A crack in this crust could unleash bursts of energy so powerful they shake the star itself, creating what astronomers call starquakes. Deeper still, below the crust, matter becomes so dense that it behaves as a continuous fluid of neutrons mixed with a few protons and electrons. This layer, called the outer core, is where most of a neutron star's mass resides. Temperatures here exceed hundreds of millions of degrees. The inner core is even more mysterious. No telescope or experiment can see inside it, and no human-made machine can replicate its pressure. We can only infer its nature through theory and observation. To understand what lies there, astronomers rely on the so-called equation of state, a set of physical laws describing how matter behaves under pressure. In ordinary stars like the Sun, the equation of state is well known, but inside neutron stars, it becomes guesswork. Do neutrons remain intact, or do they dissolve into their constituent quarks? Do new exotic particles appear? The answers determine how stiff or compressible the star's matter is, which in turn determines how large or small a neutron star can be for a given mass. In 2019, a neutron star known as J0740+6620 forced scientists to rethink what they knew. It was one of the most massive neutron stars ever measured, more than twice the mass of the Sun, yet it wasn't as small as expected. The discovery challenged existing models. Heavier stars should be smaller because their gravity squeezes them tighter, but J0740 refused to fit the pattern. The implication was profound. Either the matter inside neutron stars is less compressible than we thought, or our entire understanding of their internal structure is wrong. To probe these mysteries, scientists turned to the Neutron Star Interior Composition Explorer, or NICER, a small X-ray telescope mounted on the International Space Station. NICER measures the radiation emitted from hotspots on a neutron star's surface as it spins, allowing astronomers to infer its size and mass with incredible accuracy. In 2023, a micrometeorite damaged NICER's ultra-thin thermal shields, forcing an unprecedented spacewalk repair. When it returned to service in early 2025, the mission's importance was greater than ever. It offered a rare window into the hearts of these impossible stars. NICER's measurements confirmed that neutron stars come in a surprising range of sizes and densities, suggesting that their interiors might contain something more exotic than mere neutrons. Some scientists propose that in the deepest layers, protons and neutrons break apart entirely into quarks, forming a quark soup, a fluid of fundamental particles. Others suggested that strange quarks, a heavier cousin of the up and down quarks found in normal matter, might appear under extreme pressure, creating particles called hyperons. But there's a problem. Both quark matter and hyperons would make neutron stars more compressible, not less. If J0740 is as large as it seems, then something else must be providing resistance against gravity. Perhaps there is an additional source of pressure inside these stars, something we have yet to identify. One possibility is that dark matter, the invisible substance thought to make up most of the universe's mass, plays a hidden role. As stars move through the galaxy, they could collect dark matter particles, which might sink into their cores during collapse. If dark matter interacts with ordinary matter through gravity alone, it could help stiffen the star's equation of state, preventing it from shrinking as much as expected. This idea remains speculative, but it's one of many ways scientists are rethinking the contents of neutron stars. Another, even stranger idea involves a form of matter predicted a century ago by Indian physicist Satyendra Nath Bose and Albert Einstein: the Bose-Einstein condensate. In this state, particles known as bosons occupy the same quantum state, moving in perfect unison like a single, massive wave. If some of the particles inside a neutron star behave this way, their collective motion could create a new kind of pressure, supporting the star against gravity. Some researchers now suspect that the most massive neutron stars, like J0740, might actually be Bose-Einstein condensate stars. Regardless of what's inside them, neutron stars are pushing the limits of what matter can endure. For decades, physicists have tried to calculate how massive a neutron star can be before it collapses into a black hole. In 1939, George Volkoff, Richard Tolman, and Robert Oppenheimer worked out the first theoretical upper limit, known today as the Tolman-Oppenheimer-Volkoff limit. They estimated that any neutron star heavier than about 2 or 3 solar masses would be doomed. Above that point, not even neutron degeneracy pressure could stop the collapse. Observations continue to refine this limit. In 2017, detectors on Earth picked up ripples in spacetime from the collision of 2 neutron stars 140 million light-years away, a gravitational wave event known as GW170817. It was the first time such a merger had been seen in both gravitational waves and light. The event revealed that the combined mass of the 2 stars was around 2.8 solar masses, just above the theoretical limit. The result was catastrophic. The merged object could not remain a neutron star. Within seconds, it collapsed into a black hole. The gravitational waves from that collision allowed astronomers to test and eliminate many competing theories. They showed that neutron stars must obey a fairly narrow range of equations of state. Too soft, and they would collapse before merging. Too stiff, and they would not match the observed signal. Even so, uncertainties remain. The exact point where a neutron star becomes a black hole, where nature's final safety net gives way, is still unknown. The search for that point continues because it holds the key to something even greater. Inside neutron stars, gravity and quantum mechanics coexist in fragile balance. They are the last places in the universe where both sets of laws are equally important. Beyond them, in black holes, gravity dominates completely. If we can understand how matter behaves inside a neutron star, we might finally find the bridge between Einstein's theory of relativity and the quantum world, the long-sought theory of everything. Neutron stars are not just remnants of dead suns. They are the boundary between existence and collapse, between what we understand and what we cannot yet describe. Each one is a frozen explosion, a cosmic paradox that defies our intuition. They remind us that the universe is not only stranger than we imagine, it's stranger than we can imagine. The deeper we study them, the more questions they raise. What truly lies in their cores? What happens when matter is pushed past the breaking point? And what do these answers mean for the laws that govern the cosmos? The quest to uncover their secrets continues, because within their hearts may lie the ultimate truth about the universe itself. And if we are to find that truth, we must go deeper still, beyond the surface, beyond the crust, into the hidden core where the known laws of physics begin to crumble and something entirely new takes shape. That is where the final part of this journey leads, to what is hidden inside the heart of a neutron star. Inside the heart of a neutron star, matter exists under pressures so immense that atoms cannot survive. The nuclei are crushed together, electrons and protons fuse into neutrons, and even those neutrons may be torn apart into something deeper, more primitive, a glimpse of what the universe looked like just moments after the Big Bang. To explore that realm is to step beyond everything we understand about physics. A neutron star is not a simple sphere of neutrons. It's layered, complex, and possibly filled with exotic states of matter that exist nowhere else. Just below its surface lies an atmosphere only a few centimeters thick, a superheated mist of hydrogen and helium at temperatures near 2 million degrees. Beneath that, the crust begins. The pressure there is so great that atoms no longer have electrons orbiting them. Instead, atomic nuclei form a rigid lattice surrounded by a sea of free electrons. Deeper down, the nuclei themselves begin to deform under the crushing gravity, reshaping into strange geometric patterns, tubes, sheets, and voids known collectively as nuclear pasta. This bizarre material, with the strength of 10 billion tons per square centimeter, could be the hardest substance in existence. If a starquake were to rupture that crust, the released energy would send tremors across space. We detect them as sudden bursts of radiation, short but powerful, often from highly magnetized neutron stars called magnetars. These explosions remind us that even the universe's densest objects are not static. They strain, crack, and groan under their own gravity. Beneath the crust lies the outer core where neutrons dominate. Here, the pressure has reached the point where the difference between individual particles blurs. Protons and neutrons begin to merge into a continuous superfluid, a liquid that flows without friction. It's a realm where quantum mechanics rules on macroscopic scales, where the tiniest effects can shape the behavior of a star. Deeper still lies the inner core, the most mysterious region of all. No telescope can see it, no lab can replicate it. Scientists can only theorize. Some models suggest that inside this core, neutrons themselves dissolve into their constituent quarks, forming a quark-gluon plasma, a dense soup similar to the conditions that existed in the first microseconds of the universe. Others propose that strange quarks, one of the 6 types of quarks in nature, become stable under such pressure, creating a new form of matter entirely: strange matter. If this is true, then a neutron star's core might be a strange star, composed not of atoms or neutrons, but of quarks bound together in endless chains. But there's a paradox. If quark matter forms, it should make the star more compressible, softer, and smaller for its mass. Yet, observations of stars like J0740 show the opposite. They are heavier than expected, but not smaller. This contradiction has forced physicists to reconsider the quark soup idea. Perhaps the true core of a neutron star is even stranger than anyone predicted. One possibility involves dark matter, the invisible substance that makes up most of the universe's mass. As stars move through space, they may capture dark matter particles that sink to their cores. When such a star becomes a neutron star, that dark matter remains trapped, altering the star's structure from within. Simulations show that even a small amount of dark matter could make neutron stars less compressible, explaining the unexpected stiffness observed in some. If true, these stars are not just made of visible matter. They're cosmic hybrids, half of light and half of shadow. Another theory reaches back to the early 20th century, to the work of Satyendra Nath Bose and Albert Einstein. They predicted that under extreme conditions, certain particles called bosons could collapse into the same quantum state, forming a single, unified wave of matter known as a Bose-Einstein condensate. Inside a neutron star, some particles might pair up and behave like bosons, condensing into this new state. If that happens, the core could become a massive, coherent quantum object, matter behaving as one vast particle. In this scenario, the densest neutron stars might actually be Bose-Einstein condensate stars, supported not just by degeneracy pressure, but by a quantum unity of matter itself. These theories remain unproven, but neutron stars are already helping us test the boundaries of physics. The question of how massive they can become before collapsing into black holes has driven scientists for nearly a century. That critical threshold is called the Tolman-Oppenheimer-Volkoff limit, and it marks the final stand between stability and oblivion. Beyond it, gravity wins completely, crushing all structure into a singularity. In 2017, the universe offered a direct glimpse of this moment. Two neutron stars, orbiting each other in a distant galaxy, spiraled together in a death dance that ended in a colossal collision. The impact released gravitational waves that rippled through space and reached Earth, shaking detectors at the Laser Interferometer Gravitational Wave Observatory. For the first time, astronomers had not only heard the universe in gravity, but also seen the same event in light. Telescopes across the world observed a fading glow, gamma rays, X-rays, visible light, and radio waves, all emanating from a single point in space. The event was named GW170817. From those signals, scientists measured the combined mass of the two stars, about 2.8 times that of the Sun. This was above the theoretical neutron star limit, meaning that within seconds of the collision, the merged object must have collapsed into a black hole. But before it did, the data it produced allowed scientists to test how matter behaves under the most extreme compression ever observed. It narrowed the range of possible equations of state, ruling out many theories about how neutron stars hold themselves together. These collisions also revealed something else: the birth of heavy elements. The light curve of GW170817 showed clear evidence of gold, platinum, and other rare elements being forged in the explosion. Every ring on a finger, every piece of jewelry, every gold atom on Earth was once born in such a collision. Neutron stars, in their deaths, are the alchemists of the cosmos, creating the heaviest elements in existence. But beyond their role in chemistry, these stars are laboratories for the deepest questions in physics. They are the last places in the universe where general relativity and quantum mechanics coexist in fragile harmony. Inside a neutron star, the curvature of space-time is enormous, but quantum effects are equally important. Black holes, in contrast, are dominated by gravity alone. Understanding neutron stars may be the only way to bridge the two theories to find the elusive union between the large and the small. Some recent observations have even begun to challenge Einstein's theory itself. The timing of gravitational waves and gamma-ray bursts from GW170817 matched perfectly, suggesting that gravitational waves travel at exactly the speed of light, as relativity predicts. But other measurements, like the cooling rates of unusually cold neutron stars, have begun to rule out entire classes of quantum gravity theories. These stars are quietly eliminating ideas that once seemed possible, reshaping our understanding of how the universe works at its deepest level. In 2024, astronomers studying 3 unexpectedly cold neutron stars found that their temperatures were 10 to 100 times lower than others of similar age. The result was so extreme that it ruled out nearly 3/4 of the existing models for neutron star interiors. In doing so, it also ruled out many competing versions of quantum gravity. These stars, silent and light years away, are effectively conducting experiments that even our most powerful colliders cannot. That is what makes them so valuable. They are natural laboratories built by the universe itself, running tests that stretch the laws of physics to breaking point. Each neutron star is a question mark written in the language of gravity and quantum mechanics. The mystery of what lies within them remains unsolved, but every observation brings us closer. Perhaps in time we will confirm the existence of quark matter or dark matter cores. Perhaps we will find new states of matter entirely. Or perhaps, hidden within their depths, neutron stars will reveal the first glimpse of quantum gravity, a theory that unites the cosmos from the smallest particles to the largest structures. Until then, they stand as cosmic monuments to balance, defying collapse, yet forever teetering on the edge. They are reminders that the universe's greatest secrets are not found in its brightest lights, but in its darkest hearts. Neutron stars are the last barrier before infinity, the boundary between the physical and the unknowable. They are the closest we can come to touching the limits of existence itself. In their quiet spin, in their relentless density, in the invisible storms of their cores, they hold the answers to questions we have asked since the dawn of science. What is matter? What is gravity? And what happens when the universe reaches its breaking point? In the end, everything comes back to balance. The same struggle that shapes the life of a star shapes the cosmos itself. The constant tug between expansion and collapse, between creation and destruction. Somewhere in that balance lies the truth of why the universe exists at all. And deep within the heart of a neutron star, beyond the crust, beyond the quarks, beyond the reach of light, that truth waits in silence,